In this video, we're going to talk about the oxidation of alcohols in order to synthesize carbonyl compounds. So we're going to look at this in a generalized way again. So remember that we are not going to actually use oxygen in brackets as a reagent. This is just a placeholder that tells us that we are looking at an oxidation reaction. So in an oxidation, you can take an alcohol and turn it into an aldehyde. You can take an aldehyde and turn it into a carboxylic acid. But what we're going to learn here is that there are oxidizing agents of different strengths. And if you have a mild oxidant, mild meaning weaker, you can take a primary alcohol and oxidize it to an aldehyde. But if you have a strong oxidizing agent, it is going to take the alcohol, turn it into the aldehyde, but then the aldehyde is going to get further oxidized to the carboxylic acid. And so the aldehyde will not appear as a product because it's going to look to you like you went straight from the alcohol to the carboxylic acid. So knowing the relative strengths of your oxidants is really important. If you have a secondary alcohol, it will always get turned into a ketone. It doesn't matter if it's a strong or mild oxidant. Either way, it's going to get turned into the ketone. And then if you have a tertiary alcohol, no matter what oxidant you react it with, nothing is going to happen. And the reason why is that you have to have a hydrogen on the alcohol carbon in order to be oxidized. So notice that there is at least one hydrogen on each of these and they're able to be oxidized. The other thing that I want to point out here is that however many hydrogens you have kind of indicates the number of new bonds to oxygen that you can create. So the primary alcohol has 2 hydrogens on it, and we are ultimately able to create 2 more bonds to oxygen by using a strong oxidant. So remember that alternate definition of oxidation includes increasing bonds to oxygen. So our primary alcohol has 1 bond to oxygen. Our aldehyde has 2 bonds to oxygen, and our carboxylic acid has 3 bonds to oxygen. So overall, we are having a +2 change of bonds to oxygen, and that's because we have these 2 hydrogens. Also notice the aldehyde has this 1 hydrogen, which means it could be oxidized 1 step further to give you 3 bonds to oxygen. The secondary alcohol only has 1 hydrogen on it, and therefore it can only increase by 1 more bond to oxygen. And this is all due to the mechanism of how this works. But this explains why you can't go from secondary alcohol to ketone to ester or carboxylic acid. It is going to stop at the ketone because the ketone doesn't have any hydrogens on it. And you need those in order to continue an oxidation. So that is why the tertiary alcohol doesn't undergo any reaction. So what is this mechanism that we're undergoing here? So in this mechanism, this is alcohol oxidation by elimination. So we're going to draw our alcohol in kind of a wonky way just so we can see what's going on. Sorry, wonky, not sloppy. So I'm going to fix that. And we have to have at least 1 hydrogen, so we're going to look at a ketone oxidation here. Now, your oxidizing agents are always going to be made up of 2 parts. You're going to have something that will eventually serve as a leaving group, which is really important. And it's also going to be attached to something that we're going to call A for now, and we'll see why in a little bit. So in the first step of this reaction, the electrons on the alcohol are able to attack the so-called leaving group, which kicks out atom A. So now we have this bond to our leaving group species, and we have our atom A floating around. Now, the other thing, hopefully you're keeping track of your charges. We created a negatively charged A. There has to be a positive here somewhere. The oxygen has 3 bonds and 1 lone pair. That makes it positive. So the atom A here is going to deprotonate the oxygen. Which creates a molecule of a conjugate acid, which is why I use the letter A. And then we have a leaving group attached to oxygen. Now, this is the cool part here and why the hydrogen is so necessary. So, in this next step, a base is introduced, and the base can have a negative charge or not, but it has to have a lone pair. And the base is going to pull off the hydrogen, and we're going to do what is essentially a beta elimination. But instead of forming a double bond between 2 carbon atoms, we're going to form a double bond between the carbon and the oxygen atom, and we're going to kick out that leaving group that we added to the oxygen earlier. And that gives us our carbonyl formed through beta elimination. We have our leaving group. We have the conjugate acid of our base. So that's all of it. That's the mechanism. Now, all of the reagents that we're about to look at use the same mechanism, which is really very cool, which means they also all follow essentially the same rules, that you have to have a hydrogen present in order to undergo oxidation this way. So the first reagent that we're going to look at is for the Swern oxidation. So the Swern oxidation is really cool. This is a mild oxidant. So it's going to turn primary alcohols into aldehydes, and it's going to stop there. It's not going to move to the carboxylic acid. It'll turn a secondary alcohol to a ketone, and it cannot oxidize an aldehyde further because it's a mild oxidant. The reagents are DMSO, which is dimethyl sulfoxide, and then you have oxalochloride, which is often shorthanded as COCl with a subscript 2, but this is the actual compound here at low temperature. So usually you see like negative 78 degrees Celsius. And then you're also going to have triethylamine come in later. So triethylamine is going to be that base that gets added in the end so that you can deprotonate and do the elimination. And DMSO and oxalochloride are actually going to react together in order to create your leaving group species. So the DMSO and the oxalochloride react to create the chlorodimethyl sulfonium salt. And this is what is actually attacked by the alcohol oxygen. So I'm going to go ahead and draw this out for you. So the oxygen is going to attack the chlorodimethyl sulfonium salt. It's a salt because you have 2 ions, they're neutralizing each other. And when you do that, it's going to kick out the chlorine, which gives us this kind of weird intermediate. Where we have a positive charge on the sulfur here. Now in this next step, something kind of weird happens before you go ahead and do the elimination. So we have to actually draw out our methyl group for a second. And the triethylamine is actually going to deprotonate it. We also deprotonated the alcohol group when we added in the triethylamine. So the carbon still has 2 hydrogens on it, but it also has a lone pair and a negative charge. Now at this point, this is where the fun stuff happens. So we've created a new base. This is going to be what deprotonates the hydrogen, creating the double bond between the carbon and the oxygen, and kicking out the sulfur leaving group. So this gives us our ketone, and then also dimethyl sulfide as a side product. So this mechanism is really weird. I'm not going to ask you about this mechanism, but it is cool because you can see how even though these reagents are totally wackadoodle, I think is an appropriate word, it still follows the same mechanism that we just looked at a second ago. So our next reagent is Pyridinium Chlorochromate, also known as PCC. This is a salt formed by mixing pyridine, chromium trioxide, and hydrochloric acid. Pyridine is a heterocyclic aromatic amine. This is a mild oxidant. It turns a primary alcohol into an aldehyde, a secondary alcohol into a ketone, and again, a mild oxidant is going to have no reaction with an aldehyde. So this reagent is actually, it also does a reaction before it reacts with the organic compounds, but it's really simple. It's just a proton exchange. So what you end up with is the protonated form of pyridine, which is pyridinium, and then the chlorochromate is your counter ion. Oops. So our next reagent is the chromic acid oxidation. So chromic acid is actually a very strong oxidizing agent, and there are actually several really strong chromium 4 based oxidants. So you can use chromic acid, you can use Jones reagent, which involves chromium trioxide or sodium chromate plus water and sulfuric acid. So kind of a bizarre mixture there. This is a strong oxidant, so it'll take a primary alcohol and turn it into a carboxylic acid. A secondary alcohol will get turned into a ketone. Hopefully you're noticing that that's a trend. No matter the strength of the oxidizing agent, a secondary alcohol gets turned into a ketone. And an aldehyde will get turned into a carboxylic acid. So remember, the aldehyde still has a hydrogen attached here. It can still undergo an oxidation. Our last reagent here is going to be potassium permanganate. This is another one that you actually saw in OChem 1. You saw it reacting with double bonds, and then depending on the conditions, it either cleaved the double bond or created a diol. So this is a strong oxidant. It'll take a primary alcohol and turn it into a carboxylic acid. A secondary alcohol gets turned into a ketone. The reagents are potassium permanganate, hydroxide, water, and heat, and then you follow it up with an aqueous acid workup. But please note that you have to have the heat, the base, and the potassium permanganate in there in order for this to work. Now I want you to notice the same thing that I pointed out with the reducing agents is that oxidizing agents tend to have many oxygen atoms. So chromic acid, chromium trioxide is a piece of both Jones and PCC, or potassium permanganate. All those oxygens there tell you that these reagents are going to increase the oxygen content of the molecule. So we're going to do some practice problems. Go ahead and pause for a second. Okay, welcome back. So hopefully you paused and you worked on these problems because you need to be able to do these on your own. So in these first ones, we're going to take a primary alcohol and react it with Jones reagent. Now remember, the carbon skeleton is not going to be affected, so go ahead and draw it back out. And then you have to think about, what am I going to do to this alcohol carbon? This is a strong oxidizing agent, so it will take a primary alcohol and turn it into a carboxylic acid. If we react the same alcohol at PCC, a much more mild oxidant, we're still going to get an oxidation, but we're going to stop at the aldehyde. Now in the bottom one, you have a secondary alcohol going to a ketone. Literally all of our oxidizing reagents will do this. So you could have written PCC, Swern, Jones, chromic acid. All of these would work. Potassium permanganate. So I'm already forgetting some. All of these would work. So the last thing I want to talk about in this section is the spectroscopic evidence of a reaction. So spectroscopy can be used in a lot of different ways. It can be used to determine, what an unknown compound is, or it could be used to determine that a reaction has occurred. Because if you know what you're looking for, you can actually see some pretty obvious signs. So notice that we're looking at two oxidation reactions here. We're looking at the oxidation of a primary alcohol into a carboxylic acid, or a secondary alcohol into a ketone. So what spectroscopic evidence would we expect? Go ahead and pause for a second and ask yourself, what would I see changing in the IR? What would I see changing in the NMR, both proton and carbon? So in the IR, you hopefully recall that alcohols are going to have a broad OH stretch, somewhere between 3,200 and 3,600 per centimeters. So this alcohol, you would look at your IR spectrum and see something really big off to the far left, right? For the carbonyl, you would see the strong CO stretch forming right in the middle of the spectrum. So if we have our spectra, the alcohol is going to show up like this, broad and big. And then as the carbonyl forms, we would probably see this get depleted as a new peak in the middle, which is stronger and sharper, begins to form. And then our NMR evidence, the hydroxyl hydrogen is kind of a difficult one to track down, so I wouldn't depend on that so much. But you would see a broad shift for the hydroxyl hydrogen atom because it would exchange with deuterium. But the neighboring hydrogen on the alcohol carbon is going to appear between 3.3 and 4.0 parts per million. And then that's going to completely disappear in the carbonyl compound. So the peaks for these hydrogens is not going to exist once you've oxidized that carbon. So that's one thing that would help you figure it out. The methyl shift is going to be very, very minimal. You're not going to see a huge effect because there's a pretty big dipole here no matter what. So the de-shielding is pretty similar. The other really big change that we're going to see is the carbon NMR shift of the alcohol carbon once it gets turned into a carbonyl carbon. So for the alcohol, it's going to be somewhere between 50 and 90 ppm, but for the carbonyl, it's going to be between 160 and 215. So those are some pretty big signs. If I were trying to figure this out in a lab, I would be looking at these peaks for sure. That's a pretty clear-cut answer. And then also the IR. I think those are your strongest bits of evidence.